Okay, so very similar to yesterday, except now perhaps we're in a better seating organization so that we don't have to worry about anyone tumbling off the stage. Welcome to our second roundtable discussion. I feel like we warmed up quite well yesterday, got all of the bugs out of the system, so to speak. And today's topic is methods. What are the tools for multimodal imaging, if they do exist? What's done so far, and what is next? Who would like to start us off?
Okay, so I wanted to follow up Susan Whitfield-Gabrielli's presentation that really presents a challenge to our field. So citing the alarming increase in the suicide death rate that has occurred in the last decade, particularly in youth, age 10 to 24. These are shocking statistics. And it really highlights the need to accelerate the clinical translation of the results that are coming from multimodal imaging and other modalities. And it also highlights the need for prevention. And I wanted to ask this group of experts, so much of the imaging studies on pathophysiology of psychiatric disorders studies patient groups or studies subsyndromal patient groups. But for prevention, we need to be able to study groups that do not yet have disorders. And what you saw in Susan's presentation was a longitudinal design of studies. These studies take years to accomplish. And indeed, we do fund longitudinal studies with imaging and clinical endpoints to try to get at that. My question is, since we are studying people who don't yet have a condition, how can we improve the sensitivity? How can we improve the sensitivity of multimodal imaging techniques to better predict these long-term outcomes, like death from suicide, or like the development of serious depression or schizophrenia decades before they occur? I mean, your work illustrates some approaches to that, but how can we improve the sensitivity, either of the instruments that we're using to measure brain activity or of the analytic approaches that we use to make sense of the data that we collect, so that we can have identify every person that is on their way to dying by suicide, and every person. So for this to be clinically actionable, we don't want to miss cases because missing them can be the difference between life and death.
Absolutely, I agree. And I think that's where actually I totally agree, and I am very thoughtful about what you said, and I'm extremely passionate about what you said. And I think this is actually where we could use multimodal imaging to further predict even earlier in childhood, even in infancy. If you can look at the resting state networks and the brain networks, I mean, you can look at the subgenual cortical thickness, you could look at even in utero. I mean, we need to go earlier and earlier and earlier. We need to find biomarkers as young as we possibly can with multimodal imaging that will predict future progression. Now there's a CBCL for younger kids. The one I was talking about was 6 to 18, but now we have hundreds of data of subjects who were scanned in Boston Children's Hospital in infancy, and so we followed them for 6 years. If we can actually figure out multimodal inferences that predict future psychopathology, then we can actually do behavioral interventions very, very early on. It could be dyslexia, it could be anxiety, depression, and they've shown even in utero that there's differences that we could detect. So I think that's a really important question.
Okay. Yeah, no, actually, I think, I mean, my gut feeling, though, is that it would take a lot more data to actually come up with biomarkers. And also, certainly, multimodal helps you probe for more features. And it seems, though, that, like, there's groups, there's databases like the the Oxford Biobank, which is, or the UK Biobank, which is, it's a longitudinal study as well. And so they're attempting to capture those sort of effects over time with 50,000 people. And I think that's, my feeling is that, this hits at the central question of how much certainty. There's sensitivity that you want, but you certainly want certainty. And having even studies of 100 subjects can give results, but it might not give a high level of reproducibility that finally plays out in clinical trials. But, I'm hopeful. Yeah, and then certainly multimodal, the more features, the more measures you have, the more features you'll have to try to figure out what correlates. But another way of doing it is just trying to make models that are more informative as to what's happening, to sort of more selectively look for features that might bootstrap your sensitivity as well. Without putting Francisco on the spot, you're the expert on biomarker creation. But okay, so you're not the expert, but you have usually interesting things to say as far as what will it take to come up with a test that this is sort of like the problem in fMRI, essentially. This is it. You have cool findings, and you want to with groups or with individuals that show trends with subject populations of 100 or so, and then you want to take one subject and say, oh, pop them in the scanner and say, oh, we can predict with a certain amount of certainty, without too many false positives either, that you'll develop this if we don't intervene in some way. Help our intuition here.
Well, the first disclaimer is I've actually not trained any model that did any successful prediction of any diagnostic of any sort. But to the extent that I've helped friends that were doing that, I think the thing that was most striking was first, people were trying to do it in really small samples. And so it was possible that by accident or just by trying a lot of different methods and way of selecting features to find something that would separate patients from controls. That invariably disappeared when they tried to do the same thing on a larger sample. And then the accuracies would get to, say, 60% or something like that. And you'd think, yeah, maybe. Which suggests that probably there are lots of different subgroups of people within whatever population you're looking at. And then that's really the problem we should be trying to solve, not to distinguish patients from controls, especially if most of the time you actually know who are the patients and controls based on behavior for the types of conditions we're interested in. So then the interesting question is, are there methods for taking all this data and trying to say there are these clusters of people that are different in some significant way? And the reason I'm saying you should not listen to my advice is that I've actually steered clear of imaging to do this, and we're trying to do this kind of thing based on behavioral data, because it's a little bit easy to compile a lot of it for a lot of people from a lot of different conditions, and then trying to solve problems such as saying, can we impute missing how can we combine different sets of assays you might have for different people, impute missing values, find latent factors that explain what we see before we look at any imaging data? Because then I think we can start with something that looks sensible and then go look at the imaging to see if the imaging reflects what we found on behavioral data, which is much cheaper to acquire and of which there's decades collected already, which is kind of what we're trying to do.
Yeah, so still the consensus is that it really does take not only a huge amount of data, but a pretty good robust effect size as well.
Can I comment on that, just to be a little bit provocative? You said that we generally know who are the patients and who are the controls. I don't know that we do. So the richness of multimodal imaging approaches gives you a lot of streams of data about brain function, and to reduce it to a categorical patient or control may be missing an opportunity to understand more of the complexity within that more from a dimensional perspective. Let's take the controls, for example. They might not have a psychiatric illness diagnosed at the time you enrolled them in the study, but some of them might be on their way to developing that decades down the road. So they may not be controls. They may be future patients we don't really know, which is why I was asking the question about long-term prediction. If we had tools that would allow us to long-term predict risk for disease decades down the road, then we would be able to better screen our controls, because we would know these people are, not only don't they have the disorder now, but they're not going to get it.
Yeah, and I actually entirely agree with you. And I should have been a little bit less glib. I'm thinking of a little bit by analogy with stuff that I saw while I was in grad school, when people were coming to us and saying, hey, we have patients that have Alzheimer's and people that don't. Can you distinguish them? And sure enough, you could. And turns out that the interesting problem was not that. The problem was to say, can you distinguish controls from people with can you distinguish the people with MCI that will become patients with Alzheimer's from the ones that don't, for instance? And probably for a lot of other conditions, it's exactly as you say, is whenever we decide to, or whenever someone prepares a sample for us and says, these are patients and these are controls, maybe there are people that are borderline in some way. Maybe they will have a problem down the road and we're labeling them as controls, and that's why we end up with the poor performing models that we do. Yeah. So essentially, to talk Peter, is it's perfectly possible if you give me a sample and say, try to make something out of this that will distinguish these two groups. We can do that. But most of the time, actually, I think that's not the interesting problem, because if you say, yes, there's this you have the ability to distinguish the two groups to a certain extent. Maybe you find something that allows you to distinguish the two groups in a separate sample. That's often not the case, but people don't always try to do it to see if the results generalize to a new sample. But more importantly is even if you can, usually the models that people train are not particularly interpretable in any way, shape, or form. So if you say that, yes, there's these random entries in this connectivity matrix that separate the groups, that's really not the level of description of the data that's helpful to someone trying to understand, is this a good model or a bad model?
So just to go back to the two-group idea, so if the two groups are defined by a clinical interview, we already have that. So we actually don't need the tools to tell us what we already know. I'm especially interested in tools that can tell us what we don't know, which is what the person doesn't yet have and they're going to have. The examples you gave were from neurology, and they were from conditions where there are clear neuropathological signs of disease. And often, case in neurology, there is objectively measurable phenomenon, like a movement disorder, for example. In psychiatry, our outcomes are complex behavioral constellations of expression that change across development and may not have yet known neuropathological findings that we can see easily, and may not fit easily into categories, which is the part of the spirit behind the research domain criteria approach, to look dimensionally at domains of function that could be objectively measurable. But one clear categorical thing we do have in psychiatry is suicide. You are dead or you're not. The suicide death is a very clear endpoint. It's objective, and yet we see this increase in suicide rate. We are not succeeding in preventing the one objective thing that we have, and it's a transdiagnostic condition. It's not just about depression. It does cut across diagnoses. So I'm really delighted that all of these great minds are working on how we can optimize these tools to help clinicians do what they're not able to do right now, which is predict the future.
Well, yep. Okay. So yeah, no, I totally agree with you. And but I have discussions with Alan Koretsky, who's scientific director of NINDS, in the hall. His office is right here, about this all the time. And he's always skeptical. He's always like, you need a big effect size. You just need a big effect size. And fMRI has a pretty big effect size in itself, but then differentiating between populations in a really subtle multivariate way is a tiny, tiny, tiny effect size. And one of the only sort of measures that he could even think about with something that would predict potential problems in health that was a generally small effect size was blood pressure. And there's no other equivalent of that measure, it seems, in fMRI yet. I mean, so for instance, MRI is used clinically because, seeing a tumor is a massive, massive effect size. You can just look at an individual. And I'm the one who usually is hopeful talking to him because I say, well, if you somehow triangulate with enough small effect size and do multivariate assessments, then you can sort of bootstrap yourself up. But then also that gets noisy as well. So, but I mean, it's done clinically all the time. I mean, there's a whole science of risk factors. There's people have risk factors, and then they all add up, and you say, well, this gives the final risk factor. And maybe that's what we're looking for, and it seems like we're still kind of trying to figure out what we're actually looking for as a risk factor in that sense. So,
I think very relatedly, my gut feeling is that in the functional domain, so fMRI or EEG and so on, the feature selection step has not been solved that well, especially not including dynamical correlations or dynamics in the brain. It seems like we do a lot of machine learning to predict things, but a very crucial step that my gut feeling tells me has not been solved is having good features from the fMRI signals.
Yeah, I think my sense is that we're still sort of, there's a lot of papers coming out sort of suggesting that, all kinds of really nice studies, but they seem like, we just don't have the numbers yet to sort of test it on a larger scale and to see how reproducible it is in much larger populations. It might be. I think it's just a matter of, funding much, much bigger studies and having shared data pools to sort of test these.
So I'd like to make a somewhat orthogonal set of comments, which is that one way that we might approach the multimodal neuroimaging problem is to consider the combinations of expensive, difficult to acquire data and serially collected low-cost data. So you might imagine that let's think about a MR finding as having a comorbidity with an EEG finding, and I can come up with good ideas for that right away. We look at some structural abnormality in the brain, connectivity, early on, which may convert to depression that's detectable through the addition of another modality, such as EEG changes in slowing. And so what in effect happens is you do this expensive test once and early, and then you consider your multimodal imaging as a series of less expensive tests done as needed, where they can still, in the sort of generalized multivariate framework, add information as weak indicators.
The other thing I wonder about is a lot of the tests that we do, thank you, a lot of the tests that we do require cooperation on the part of the subject. And I wonder whether we've actually got the right tools at our disposal to test some of these patients, because they're the ones, probably those interesting ones, are going to be the ones in the neuropsychiatric disorders that are going to be uncooperative, and that you're not going to get a good, clear result because we require cooperation in our methods. How do we go about it? Well, I think we need more robust data gathering methods that might be able to sift out brain signals from non-brain signals. And I think there is hope, and I see hope in two dimensions. One is on the inexpensive technology side of things, as Mark was mentioning. Portable EEG systems are now starting, some of them are quite robust, and they can cope with a lot of artifacts and sources of interference that some of our lab systems can't, because they have very high input impedances. And they're dry electrode systems, so you don't have this preparation anymore that you used to have. So that might be a good thing, and that's something that can be used in rural communities. You don't have to go to building 10 to get tested. So there's that aspect. MRI technology, I think, has a long way to develop. I remember the first time I saw images of motion-corrected structural anatomical data, which is amazing what you could do. You could just lie there in the scanner and move your head like this and you could get perfectly good anatomicals. Well, we need to be thinking out of the head coil, if you will, pun intended, about how we can get functional data that are compromised by movement. You know, have maybe some sort of data acquisition strategy where online you're detecting, okay, was that last volume a quality volume that I detected? Okay, maybe I need to excite the tissue and deliver another excitation so I can get another volume that's a better quality one, and have that maybe tied to your activation task. It's like and what I'm suggesting is not rocket science. When I look at my developmental colleagues who study gaze contingent paradigms, and Molly's not here, but gaze contingent paradigms, the test can't go on unless the subject's cooperating and looking at the stimulus. So I think there are ways that we can be creative about how we design our activation tasks, couple them with our data acquisition methods, and just think out of the box about it.
Also,
Sorry, I think Laura Lewis.
oh yeah.
I really agree about the point about data quality, and I think it also speaks to kind of the other issue with these really large data sets. Large data is obviously great, but if it was acquired at a resolution that doesn't capture the information that you need, then, you know, if there was a problem with a mental health disorder that was at the level of cortical layers, and you do a standard fMRI experiment with 2 millimeters, no matter how much data you collect, you'll never manage to distinguish that effect. And so I think from the technology side, pushing the spatial and temporal resolution of each of these methods could be really powerful, whether it's with ultra-high field MR or with integrated PET MR, or, you know, better kind of localization of EEG and MEG signals, because right now a lot of what we want to understand may be in these tiny structures that, you know, aren't really being measured.
Yeah, I completely agree. So yeah, I talk about big data, and I think there's a place for big data, but I actually think that, and also, you know, from my discussions with Alan as well, is that the real innovation still that remains is in the acquisition and in pushing the limits of resolution, temporal resolution, spatial resolution, doing clever things, or even trying, you know, things like that are therapeutic interventions like real-time neurofeedback. You know, I think that there's more information in the signal that are potentially bigger effect sizes. I think that's where it's worth investing equally much, if not more, than throwing data into large data pools, which has a place as well, though.
Yeah, and I just wanted to second both of those points. And that is exactly what the BRAIN Initiative is seeking to fund. Basically, the leveling up our game in terms of being sensitive to these smaller units of analysis. I agree there needs to be specificity as well, but if you can't measure it at all, that's a non-starter. So that's why I use the word sensitivity. But I really would like to go back to your point about feature selection. And I was wondering, those of you who are experts in this area, I was wondering, you know, if Bob had ideas about how the acquisition packages and analysis platforms can help. I'm wondering, are we doing data reduction steps that are hindering feature extraction, or just say more about how we're going to fix this issue of feature extraction?
So I think it goes in the same direction as what you said before with Alzheimer's. We see things in the brain, right? So we have a feature that as humans could see, and what you said is that maybe the signal of some diseases of the psychiatric domain aren't even in the signal. But then maybe one thing could also be that, you know, if we, for example, only look at static fMRI correlations in terms of dynamic, and I know everybody's doing that currently, but just as an example, if you only look at static, you could never find it. But if you have the right feature selected from the MRI signal, then only you can have a large effect size. So obviously it would be great to have something that we can really see, at least in some patients where we see differences, and then use that and leverage on it and then put it into a machine learning algorithm to harvest that. So it feels to me sometimes that in the psychiatric domain we are currently blindly fishing for things without knowing what to look for. Of course, there are exceptions. But, yeah.
One quick example of how we're sort of shooting ourselves in the foot in the sense of just looking at fMRI activation. You know, people put in a model function And it's a, hemodynamic response function, convolved with a boxcar function or something like that. They've been doing that for years. But if you really look at the data, there's all kinds of other time-locked responses that don't really say that the hemodynamics are different, but the underlying neural activity might have different shapes, all kinds of different shapes. And so we're just throwing that away at the first step. So I can imagine that you can do some sort of naturalistic stimuli or other sort of resting state and sort of iterate, like you were saying, between some sort of broad net of looking for features that might correlate with what's going on, that then iterate between a model that kind of grows. And I think that would help pull out things that we haven't seen before. So that's one idea.
So I do want to hop in both because we got a question online and it was pointed out that we were bad at asking the questions, but it was also a question that I was going to bring up or face the wrath of my neuropsychology mentor, which is that feature selection doesn't necessarily have to exist just on the imaging side. And so one of the characteristic flaws or shortcomings of a lot of imaging studies and a lot of psychiatric diagnostic studies is the lack of neuropsych measures. And so like CBCL is a great measure, but it's one of many, many measures. And as we're trying to get at depression, we also need to make measures of, say, resilience, and we also have to make measures of the fact that not everyone who has depression attempts to commit suicide, and not everyone who attempts to commit suicide is actually successful. Actually, the rate is about 33 failures per 1 success. And oftentimes, people do repeat and do succeed in these things, but there are some predictive measures that we have just from behavior. And I think that in addition to this better voxels, better triangulation, more features in the imaging world, we also need to be talking about how we are measuring the behavioral realm and the genetics realm, because depression is heritable and suicide rates is based off of both our genes but also our family and our social environments. And suicide rates are much higher today, we know this, than they were in the past. And one of the driving features of this is, I'm not going to say Facebook, but sort of the social comparison of everyone's lives to everyone else's lives. So there are these additional things that I just want to remind us that not everything is putting someone in a scanner.
Okay. So feature selection is a really interesting topic in general. In the machine learning community, a lot of people think about this rather differently, which is the problem of over-dimensionalized data, where you're looking at too many features, and in the end, you end up in trouble. And so in neuroimaging in particular, we usually have a problem more of dimension reduction than dimension expansion. And here you're arguing for something else a little bit, which is an expansion of the set of features that we use our intellectual priors to go ahead and say, this is a meaningful feature to bring into the data. So I'm just going to ask that we kind of be careful with that. And then in the context of machine learning, there are a series of relatively well-defined and stable tools for dimension reduction or feature selection. There's the minimum redundancy, maximum relevance criterion that people use. ICA is actually a relatively good tool for dimension reduction because the statistical independence tends to be supportive of multivariate analyses. So within modality, how do you control the features? And these are editorial about the discussion, not necessarily a motion towards a particular direction.
No, but sorry, Holly, but I'd like to actually answer your question, because I think the problem is not per se doing feature selection. That's something that, as Mark is saying, that's easy to do, and there's umpteen criteria we could toss at the data. And as the data sets get multimodal, there's just more features to pick from. And the issue is a little bit different. It's that even if we assume that there's no problem with the heterogeneity of the people that go into the sample, even if we assume that the labels were actually reliable enough to say there are two groups, we should understand what's different between them, the problem often is not, even if you can make a nice model, the question that can actually distinguish them in some meaningful way or can predict the thing that you want to predict down the road, you still have the problem of saying, why does the model do what it does? And this intersects with feature selection in the sense that some of the methods that Mark is describing transform the features into a space that might be more interpretable because they aggregate lots of spatial information or all the connections for a particular ROI. The thing I wanted to throw in is, to me, that problem is actually more important, and that's where bringing in the priors or talking to the domain experts makes sense, because often it means that you can transform the data in a way that should you have a model that is successful, that model also tells you an answer to a question that the expert actually has.
Yeah, so let me just hop in on that. Michela Franti has a new funding opportunity on explainable artificial intelligence. And so if you can't explain it intuitively, that might hinder our ability to learn about the scientific aspects, that can hinder scientific understanding. But even if it's not explainable, it might work. And it might be useful clinically, but I take your point. I want to bring us back to Peter's comment about the neuropsychological testing and the richness of phenotyping. And that's why I brought up the research domain criteria, because that platform means for us to look at domains of function which are objectively quantifiable across levels of analysis, from the genetic to the molecular to the circuit, which is where a lot of this discussion lives, but then going on to the behavioral expression and clinical symptoms, and to look at that across development. And that's rich. That's a rich multimodal data set of things that we can measure to have more features on the clinical side and on the phenotyping side to mate up with what you get from the imaging side. My question is, so even when you have tags, like this person has a diagnosed depression, they don't have the same severity of depression at every moment and every second during which they're being scanned. So their state is changing. And I'm wondering, in all of the imaging studies that you're doing, what do you do to assess the state of the patient during the scan itself? For longitudinal, you might do a clinical rating scale and say their depression severity is 21 on a 24-item Hamilton score, something like that. But that is also a lot of data reduction, because that's averaging across different types of symptoms. You can get a score of 21 with very different types of symptoms, and yet we call these people having the same severity. Is there anything done to assess the state of the subject during the scan itself, either through facial expression, that you might be, have a camera on the person's face, you could look at the affective, nonverbal affective expression on their face, is anything done during the scan itself? Yes.
I think this is an excellent question, and I think all of the things you mentioned are critical. We have done dynamic connectivity because, as you said, the brain state changes. If you're doing resting state connectivity, for instance, we've looked at people with major depression, and we looked at how the brain is modulated in terms of dynamic connectivity over, say, a 10-minute resting state scan. But there's many other things that you could actually collect as well to look at the temporal variation during that scan. So I think it's an excellent point.
Also on that note, the other thing that I don't think there's anything very robust on this yet, but in the behavioral realm, there's been a lot of stuff on using free speech as a behavioral measure, and some of that, including some work Emily Finn is doing, is trying to bring that into the scanner. So if there's differences in how people speak freely depending on behavioral state, that could be a very powerful measure linked in to neuroimaging.
Yeah, I'll just second that. So natural language processing, analyzing not only you can analyze the thought process as well as the content of speech, and really beautiful studies using this to try to predict things like conversion to psychosis. We'd like to see these things replicated, also trying to predict likelihood of self-harm. So yes, that's a lot of advances in that. Also digital phenotyping, capturing moment-by-moment changes in the affective prosody of speech, as well as the nonverbal affective expression and facial expression and movement, and these digital phenotyping trackers to look at geolocation and how much social sensing, how much you're texting, how much you're on Facebook. All of that can be quantified because your phone knows that. Google, Apple knows, Facebook knows what you're doing, might know more about you than your psychiatrist.
So isn't Time Insuls, that's Time Insuls has a company that's having apparently an app that's hopefully will be tracking that sort of thing. But I agree. I completely agree.
Sorry, I don't want to hijack what is absolutely a very productive and interesting discussion, but I'd like to try to involve some of the speakers today in the discussion that maybe could be separated, at least temporarily, from the topic of, say, clinical depression, suicidality, and things like that. And so maybe the prompt I'll give, particularly to sort of the app developers, if you will, is this question that we come up with a lot at the NIH, which is about learning curves. And so there are a lot of people who say we need to be using BIDs and we need to be doing this and we need to be using these sequences, but the 99% of the field or 98% of the field is still doing imaging in a very simplistic way, which is, you run block design, you put all those subjects together, you run an ANOVA, ta-da, you get results, and that's what they write up. Is there something that the NIH could be funding? Is there something that we could be helping doing as app developers, as programmers, as scientists to try to move the field to better practices and whatnot?
Maybe if I can comment on this, the best way to, just to give you a concrete example of this, we are having this conversation with Robert, I think yesterday, about the fact that maybe people still use 3T scanners and not 7T scanners because the tools don't work as well with what they have on these types of more advanced images. And on the flip side is that if the people who were writing these tools would have access to the data early to kind of co-develop, which I always ask, okay, how people can ask me, how can I contribute to M&E? I said, can you give me one data set that addresses your use case? I can make a tutorial. And this is the types of things that can be very valuable, that the problems are exposed, so the toolbox or the app developers can also learn from the use case because we only have one bias sample, which is the colleagues that we have next to us. But if we can have more sharing of issues in order to adjust the tools to specific use case, that can be very beneficial, I would say.
Something else which I think would definitely help in increasing the usage of new technologies such as organizing data in bits would be to support projects in outreach, in maintenance. We have a lot of smart people that are highly motivated and working on the technical aspects, on the methodological aspects. But at a certain point, we also need people that are able to translate this into a language that is understood by the people that are doing the clinical research. So yesterday we already identified that communication between people working in the different silos, that's important. And it's not necessarily the people that are doing the technical development that will acquire the skills to translate this towards the clinical researchers. It's not necessarily the clinical researchers that are going to understand how GitHub works. We also need the people that are really working in between. So that's for example, where maintenance, that's where training comes in. And that in itself is perhaps not a scientific goal, but it is something that is necessary as to oil this whole machinery.
I would,
I just wanted to say that we teach AFNI boot camps a lot in various strange places sometimes. And there's a lot of what I see, what you're saying, that there's or bog standard stuff. And there's a lot of problems because some people simply have no idea what they're doing. And so they just do what they think they've read in papers, and then which are not always right in the first place, or are clear anyway. And then they apply it to data that's crappy because they have their scanners there are not maintained well, so that they have a lot of artifacts in them, so that especially when you do correlations, for interregional correlations, artifacts are death, and that it is the people that work, places they don't have anyone that can help them with either of these things, which are two separate things. Methodology the scanner and methodology of the analysis, this is difficult because they have bad data and/or they just don't know what to do with the analysis. Right. I mean, they may have heard that they should use CompCore, but they do it. They write their own program to do it or something, and then people make mistakes like they blur the data and then they extract the white matter components, which means you're blurring in gray matter, and so now you're doing global signal regression, which was your point of avoiding it. I mean, they don't know, and that's a simple one, but it's easy to forget. And so when you say helping people get better, and then there's pulse sequences, right? Pulse sequences, they don't have MR physicists in many cases. In China in particular, which isn't really the direct concern of the NIH, of course, but in China in particular, they're saying, oh, it's very hard to hire MR physicists because they all go to Europe because they get paid more, so because there's one place that there's data, and I looked at this, did Instacore on it, and it was just shot full of artifact. I mean, you don't normally see like correlation patterns that are like crossed like this, and stuff. It was a multi-band artifact, I think. But they said, you've got to get someone to fix your scanner. No, we can't do that. They don't know how to do that. The manufacturer says it's fine, so that's all they do. So, and that was an extreme case because that image was burned in my mind about how bad this data was. But in a smaller sense, this occurs all over because they don't. Places that are actually reasonably well known, they don't properly keep their scanners consistent. Like we do at the NIH, where you check a pseudo fMRI scan on a bottle of water every day to see if the signal noise ratio is changing, because that's not part of this manufacturer's protocol, but it's testing a stand-in for human data of the kind you care about. Most places don't do that.
If I just can comment on this, what I see happening quite often, maybe not in MRI because MRI is used for many other things than functional MRI, but people would buy an EEG system or an MEG system or a NIR system and came up with the conclusion that it's basically sucks. That's not a good equipment or not a good modality, but because they don't make sense of the data. After 2, 3 years, 4 years, nothing comes out. And it's not really a problem of the acquisition or the problem of the device in itself, as you pretty much alluding to. It's a problem of that there's not enough people who know how to acquire good data and process good data. And part of maybe I would see my responsibility as an app developer, I think we don't invest enough time to give the tools so people can do quality control, can get a red flag or something that will show them that there's something wrong and what is wrong. And so people don't, it's always probably easier to do or nicer to do the fancy analysis steps, but all the quality control, all those things that we can provide to users in order to suggest that there's an acquisition problem or there's this or this problem, potentially could improve this.
Well, maybe there should be a traveling cohort to give people boot camp in how to operate their scanner, as opposed to the analysis, which is what we do, right?
Yeah, we all do this, but it's just that we cannot travel all the time. We're already traveling too much.
Sorry, I just want to interrupt. Mark's had his hand up, and then Laura.
So I just want to suggest maybe an actual fungible approach to this, which is that the NIH might entertain applications about developing best practices guidelines that are actually supplemented by somebody who offers the service of analyzing the data remotely from these various scanners. So essentially I say, you're going to scan this bottle of water, which you can buy at, Thrifty because it's got the right container in it, it's the right shape. You go in there, these are our expectations from the scanner. I go back and tell you whether your equipment is operating properly and also give you consensus guidelines about how you go ahead and do these analyses, right? So that you can at least offer yourself some protection against poor data collection as the reason you have experimental failures.
I read a great opinion piece recently, which I'm just repeating here, but arguing for the role of professional scientists who are consultants. Because often we rely on just a bit of information here or there that we can get from somebody who's also incredibly busy. But there's many very well qualified scientists who could take on a technological consulting role of kind of going from lab to lab and really helping in a more in-depth way instituting these practices. And then if there was a kind of system to kind of pay these people for their expertise and set it up as another career path, I think that could be really productive.
So I also want to know, some of this stuff already does exist. So like there's Mri Qc, which allows anyone in the world to upload like their MPRH, their anatomical scans into a common database. And it will tell you if your MPRH scan looks really different from people other places. So that if you have your data right now, you could do that. And there's really no, there's no external pressure to do that, but if people care about the data, these resources are available. The other thing I want to make a note on this, though, is we talked about siloization yesterday. One of the silos is sort of the analysis methodology versus acquisition methodology. And I have heard from multiple, especially as we're getting to the big data world, multiple analysis methodologists who are like, if the data sample gets big enough, all the noise will average out and we don't have to worry about it. And I've also, seen, especially with non-methodologist end users, if someone bothered to collect 1,000 subjects of data, they must know what they're doing, and we can trust their data. So, like to talk about the biggest elephant, like the original Connectome project data set of N of 1,000. It's a great center, great group. They manage all those scanners, and data quality varies quite a bit across that sample because it's human data, and there's no such thing as perfect data. And this idea that you can't just sort of trust the data, that you actually have to understand it and know it, and have the people who can do those stuff is critical. And we can't sort of silo away that, like, the analysis people don't have to think about acquisition, and now acquisition people don't have to think about analysis, because they interacted pretty much every step of the process.
I'm just going to hop in from an online question, which, again, coincides. I swear I'm not making up this person, but their name is HM. But this says, I think tool developers are often guilty of expecting average users to become expert computer scientists on top of their original training. Anyone want to discuss?
So that goes a bit in line of what I wanted to say for a while, that I see myself as an intermediate person, so I'm echoing what you're saying, trying to bridge the medical world with the experts world, and also what you're saying, there is Mri Qc online, but I think the problem is that the people that should use it don't know about it. So, and going back to your question, maybe what could the NIH do really is an easy way to educate people. And speaking personally, the way I keep up to date is really Twitter. So it might be a weird suggestion, but I think people that are on Twitter at least find out where the field is moving, and there might be different ways to do that beyond Twitter. But something like going to conferences, having a oral exchange, or something like a fast medium like Twitter, where you keep up to date what's going on, what is out there, even makes it possible to be aware of something like Mri Qc. So I think that could be something to improve, get more people on there.
Just getting back to that question and training, I think we have to think about how we train scientists, because we're not doing the right job. Because people who are coming through psychology degrees don't have the tools to do these sorts of analyses. And I'm not a developer, and I'm one of these people in between, and that really, really frustrates me, because I get people in the lab who are incredibly intelligent, incredibly bright, haven't had the educational preparation to deal with working in a social neuroscience or a cognitive or a systems neuroscience lab. They can't code. This is basic. This is the digital age. We're a fifth of the way through the 21st century. They can't code.
So just to I just wanted to add
I just want to add to what was just said, and that one of the ways that we might fix this problem is is extending the training periods for our students. I mean, I don't know how many PhD students that I've had that had to finish what I considered early because they had 3 years or 2.5 years or maybe 4 years, but usually not quite, in the training program, that just simply wasn't enough time to give them the skills that they needed to do this type of multimodal work. They need to code, they need to understand MR, they need to understand EEG, they need to understand maybe behavioral measures. There's a lot of things that people need to know in order to do the kind of work that we're talking about really credibly. And we're simply not training them. Just what Ines said, but I think we could solve that problem if we extend our training grants, and that's why I think that perhaps NIH could help a little bit there with the funding for the training programs.
I would advocate we start advocating in high schools and at undergraduate level for better training so that we don't have to remediate, because that's what we're doing, we're remediating.
I'm going to call on Dan and then on Ted.
So on the issue of undergraduate training, here at the NIH intramural program, we have a very large program for recruiting research assistants that finish their undergraduate. So every year I look at this huge database we have with hundreds of psychology students from all universities across the whole country. And I've noticed, particularly in the last 5 or so years, there are more psychology undergraduates who have taken a specialized course in fMRI than have taken a course in programming. So that means more psychology departments have invested in sort of creating a whole curriculum around fMRI without having a parallel class which gives them the skills to actually do what they're being trained in doing. So there are a select number of departments that are offering sort of, like you don't want to send people to a computer science 101 course in a computer science department necessarily, because it's not ideal, but there are some departments that are really pushing towards what a true, data analysis course would look like, not statistics, but data analysis, computer science course would look like for psychology departments. And, efforts to sort of develop those courses and spread them and make it easier for new universities to teach them, I think would make a game changer. And I'll say that completely selfishly from trying to hire people year after year who come in with those skills, and year after year hiring people who have to train in those skills.
This is switching off of the education question a little bit, going back. But I mean, I was thinking about one of my personal experience and then something Alex said this morning with you get collaborators before you get end users in terms of developing these projects. And unfortunately, in my lab, it's the opposite. I have so many end users and nobody to develop the code. And the reason is because when we get funding, right, someone writes a grant to study suicide or depression or something, and they put me on for 10%, and I do the scope of work, maybe write them new code or something like that. But then the grant ends, and this code exists, and there's no way to get it out into the public domain in terms of to get it solid, robust enough that other people could benefit from it. And so I was just kind of thinking along those lines, because that's how I end up being funded, is all these co-investigator studies, but not the money to kind of bring it to more general use. And so I was kind of thinking in terms of the NIH, right? So we've had this huge push towards databasing, where there's supplements. If you're collecting data, we'll give you an extra couple $100 per subject to put it in our database, like kind of a supplement, sort of no questions asked sort of. What if there was something like that in terms of you've developed new tools for a project, we're going to give you money to kind of translate it into one of these NIH-run databases to make it more publicly available. And because that's where I end up with this whole backlog of projects tools I'd love to see developed for more people that I've already published the papers, but there's no money to do it anymore.
I also just want to add, as the possibly second or third youngest person in the room, if we make PhD programs longer, we need to raise the salary of graduate students. I'm sure that I'll get lots of thank you emails after this.
at the serious risk of talking too much, which I do, I want to be much more sympathetic to that user's question. I think that it's absurd to imagine that everybody who does fMRI has to learn to code. And I know some very, very wonderful scientists who use fMRI all the time and make serious and important discoveries who couldn't code to save their lives. It's the wrong thinking. What we have to do is finish our software projects, not just come up with an idea and write it in the paper. We actually have to produce tools that people can use. And I think the burden is on the developers to make, accessible tools, not on the users to figure out how to use inaccessible tools. And I also have to say I love the idea that we should train people longer, but I assure you my parents argued about whether or not I was sufficiently trained, or at least the teachers who taught me were always advocating for increasing the curriculum load. And anybody who sits on a curriculum committee at a university always knows the pressure, is, well, our kids don't know how to, solve trigonometry problems by the time they get their PhD in psychology. How can we let them out? And this is also unrealistic. And if you really want to think about augmented training, it has to be lifelong training. It has to be, some way in which we take established people and give them an opportunity to learn what's current, not to enforce that people by the time they're 23 know everything they need to know until they're 70.
Maybe something akin to continuing education classes?
Following up on your point, which is very well taken, perhaps if we don't extend the amount of time that we give our students in our PhD programs, we should teach them differently. We should teach them tools of collaboration. We should teach them, we should expose them to other techniques, perhaps more superficially. But nonetheless, what we're doing is teaching people to be expert in one particular area, and what we're asking the field to do is grow in these multimodal techniques. And so we need to prepare our students in one way or another to do that. So if we don't extend the time in graduate school, at least we can use the time that we have them in graduate school to be more, I like the word Renaissance scientists, to think more broadly about what we do and what the tools that we have available to us can offer.
So this morning, Alex showed some photos from the MNE bootcamp that we had 4 weeks ago in Boston, and so I really enjoyed it because it was not only an attempt in getting new codes implemented, but also an attempt at training new people from different fields in a style of working. So this was really like a very interactive style of working, having a hardcore GitHub user explain a psychiatrist on how this works. And I think both sides learn from such an interactive style of working. And that's what I have in mind with team science, is that we should bridge these gaps, because I don't expect that we'll have super PhD students in the future. There's just limits to what people can learn. But there's, I think, the social structure that we can further exploit in terms of specialization and working together, and that's also perhaps where we need to work together more across universities rather than within universities. So having technical support scientists that are actually traveling around to share the knowledge in the same way as I'm sharing my knowledge at a lot of different universities already. I think that's what we should aim for, like more collaborations.
Well, we talked about, grad students and training postdocs and stuff, but what about, like, you think about junior faculty, right? I mean, maybe they get a K award, and that whole point is like education, you're training, and you get a sponsor. But then, in the institution, you're pushed, get an R1, right? Because you're not going to get tenure unless you get that R1. And once you've gotten that point, those kind of K award mechanisms no longer apply. And so now they're on their own. And so if they haven't picked up those skills at that point, you're kind of on your own. And so maybe there's a way to kind of extend that continual learning, but kind of beyond that initial junior investigator, new investigator, because the technology is continually developing. And I think a lot of the people that are having trouble with, applying the fMRI wrong or something, it's because fMRI came in later in their career and this is a new field for them and they're, trying to write an R01 on something they have never really been trained on. And I don't know, maybe there's a way to kind of get that kind of mentoring. I don't know.
K-24. So we do have a mechanism for mid-career scientists to allow them to train in a field that's new to them and also support some of their time to mentor others. But I know that you're suggesting something that might be broader, but I just want to be sure that people are aware about the K-24 mechanism.
But it's a sort of a more minor, it's the best you can do in terms of, but like in terms of the institutions, right? They're pushing for, R1s and stuff like that. I don't know. And my impression of the K-24 is not many people really apply for it, and there's not that many awarded and stuff like that. So I don't know, that could be wrong, but.
Okay, so we're running out of time. If I wanted to bring this discussion full circle, my takeaway points for anyone still on the line at home would be that in order to move forward on biomarkers and trying to address major clinical disorders, we need to address them both by coming up with better features, better measurements, better tools, identifying what we should actually be measuring, and by perhaps making software that is more accessible to users. And I think the one thing that went sort of unspoken this entire time was also trying to train people to be better scientists and ask the right questions in the right way, because that can, as was stated in multiple talks today, be somewhat divorced from this idea of people who are really good at coding. Sometimes the people who have the really fantastic big ideas are the people who are high enough up that they don't do the sort of nitty-gritty anymore. And I'm not saying that that's necessarily ideal, but I think that there are many issues that are going to go into multimodal imaging in the future, particularly to address these neuropsychological and psychiatric disorders. I think it's sort of this multi-thronged approach.
This is more of a specific comment as opposed to a general comment, but relating to what Mark said. I think the idea of like teaching something like a data science course or a computation course, it's not about like, we think you should learn this, you should, this is like a front pushing. I think there's a huge demand. One of my grad school colleagues, Brad Wojtek, who's now a faculty at UCSD, he put an intro to data science course in their cognitive science department. In the period of 3 years, it went from an enrollment of 30 to over 300. There is a massive demand from the students that know they want to get these skills. And the idea that, if more universities had the resources and funding to develop these courses and offer these courses, I think it's not a matter of like convincing people to take it or requiring them. It's just if you make these courses well, there's a huge demand from students to pick up these skills because they know what's useful to become a successful scientist. And this is one of those skills that can help people along that way.
Anyone else have any last comments before we wrap up for the day?
If there's any AFNI users here who have not ever received an AFNI pen, I have a few. I have a few in my briefcase.
And I have many stickers if you want.
Yeah, go ahead.
K-24, I just looked it up. It's open mid-career to do more clinical research. It really doesn't address the problem of taking researchers and letting them learn new methods. There may be some other mechanism, but if there's not, it would be nice for NIH to consider one.